All right, so this is the beginning of the second half of part 4, in which we discuss the inequality between current and dissipation. The inequality basically says that whenever you have non-zero current, you also have non-zero dissipation, non-zero loss. And here we consider operations in a non-equilibrium environment. And as I said before, the topic is based on a recent work by Naoto Shiraishi, Keiji Saito, and myself. But I think this is elementary and interesting enough. Okay, so let me first discuss something that I call the improved Shiraishi-Saito inequality. And this can be proved in rather general setting, but here we consider a general Markov jump process as we are doing. So these are just review of our notation. This is transition rates. We make this crucial assumption that whenever you can go from J to K, you can also go from K to J. And this is transition rate matrix. This is escape rate. This is master equation, and we consider a general asymmetric jump quantity. And this is the standard expectation value. Of course, it gives the rate of this G. Okay, and since we discussed this many times, so we abbreviate this expectation value like this. Okay. Okay, so now I want to discuss a general lower bound for entropy production rate. What is entropy production rate? Well, it's defined like this, and it consists of two different terms. And first of all, this is simply the expectation value of the entropy production in the bath. Okay, so okay, and the first term is, again, this is simple. This is just the time derivative of the Shannon entropy of the system. Okay. Of course, P is the probability distribution of the system. It's time dependent, so we have time dependent Shannon entropy. Okay. So this describes a change in the entropy in the system, and this describes the change in the entropy of the bath. And the two terms are, I would say, very different. Okay. And this term, especially when combined with detailed balance condition, looks more or less thermodynamics. Okay. So this just usually this describes the entropy, the increase of the entropy in the bath by using this delta S equals delta Q over delta T formula from thermodynamics. So this is, so to speak, more or less thermodynamic, but this is more statistical mechanics, or more information theoretic, right? So we have this is Shannon entropy. And as I said before, Shannon entropy happens to be identical to the thermodynamic entropy when P is like the canonical distribution, when P is a special distribution. But in general, this Shannon entropy does not have any thermodynamic meaning. So, but anyway, we call it entropy, and we take time derivative, and anyway, we sum these two totally different entropy productions together to get the total entropy production. But it happens to be, it turns out that this sigma t is mathematically, theoretically a nice quantity. And the basic lower bound that I'm going to prove is this. Okay, so I prove that this sigma t is lower bounded by this quantity where we have this transition rates and P. And actually, this combination is familiar. If you recall what we did in part 2, page 32, actually, we have everything. But anyway, let's go to part 2. So this is good old part 2, and we discuss probability current. Okay, and this quantity, if you define this quantity, then we have this continuity equation with probability. Okay, so this is the probability current. So let's go back. Yes, so it's here. But you see that this probability current is something we exactly have here. So here we have probability current squared. And here we have something very similar to probability current, but we have plus sign. So yeah, so we consider probability current, but we sum all the probability currents here. Okay, so but anyway, this and of course this is positive, and this is of course non-negative because we have squared here. So what does this mean? Well, this roughly said that whenever you have non-zero probability current from J to K, then of course this is non-zero, and of course this is non-zero. So this sigma is non-zero. So this inequality means that whenever you have non-zero probability current, you have non-zero sigma t. Non-zero probability current means that your total entropy production is positive. Your total entropy production must increase. Okay, so I want to prove this first, and the proof is very, very elementary, and a bit complicated, but very elementary. So let me show how you do this. So we have these two terms. We simply write down the definitions. So this is the Shannon entropy. So you take this time derivative. So you have pt here and here. So you get two terms, this and this. But look at, so you differentiate this with respect to time, you get this. And but now these p's cancel, and you get sum of p dot dot kt. But of course, since sum of pk is always 1, this sum is 0. So this goes away. And so you only have this part. Now you plug in the master equation to write this like this. Okay, and this is okay. But now I want to rewrite this further like this. Well, first of all, you have minus sign here. So this is the same as this. Okay, but why do we have this? Why do we have this pj? Actually, this quantity is 0. Why? Well, here you have we have only j-dependent terms here. So you can just sum over k freely. But if you sum over k, you must get 0. Okay, so this is just 0. Okay, so we simply added this thing, which is 0, to get this expression. Okay, so now we look at this, the expectation value of the entropy production in the bath. Okay, and this is just the definition, our familiar definition. This is theta. And now so this is only complicated notation. So this is equal to this. So we use R to write it like this. And so we have J and K, and this is summed over J and K, which are not equal. But if you look at the term 1k and j are the same, and then this gives you 0. So you can add this diagonal term to write it like this. Okay. Now we have these two terms which have common sum, and this and this. So you just simply sum over these two things to get this. Okay, and now again, now if you look at what happens if k and j are the same, and then this gives you 1 and log 1 is 0. So you can again omit this diagonal term to get this. Okay, sum over j and k which are not equal, and this. But look, this is a very nice expression. So rkjpj, these are the same. And this is something different, but this is almost the same thing with k and j switched. So we have two indices kj, but this precisely looks like the definition of the Kullback-Leibler divergence, the relative entropy. Okay, and since the relative entropy is non-negative, you can show that this is non-negative. So this is a very important, well-known expression, and from this you see that sigma t is non-negative. This is a very important result. Since this is the total entropy production, this shows you that the entropy cannot decrease, the second law of thermodynamics, one form of second law of thermodynamics. Okay, and so as I said before, on this term and this term, these two terms look very different. But if you sum these two terms, you get a quantity which have this very neat expression. Okay. Okay. So to prove our inequality, we further do this. We further rewrite this like this. Well, this is almost nothing. If you switch k and j here, then this and this switch, so you get minus sign. So here you have the same thing with k and j switch. So these are the same thing. So, but we add the two same thing and divide by 2. Okay, so we have this expression. So let's go to the next page. So this is our expression. But now, as you see, we have here we have this probability current. And I claim that this can be lower bounded like this. Why? Well, this has a very simple form again. Here, this and these are the same, and this and this are the same. So this has precisely this form, 1/2 a minus b log a over b. And then I claim that this is just a very elementary inequality. I claim that this is lower bounded by this for any positive AB. So how do you prove this? Well, you can, yeah, you can prove this in any way, or you can convince that this is true by just plugging this into mathematical something and drawing a graph. But okay, let me see quickly see how it goes. So first of all, you note that this is invariant under the exchange of A and B. If you switch A and B, you get minus here, you minus here, and this doesn't change. So we can safely assume that A is not less than B. Okay, and then these are both positive, and it's easier to treat. And you see that this desired inequality is equivalent to this, or this inequality. Okay, and so I want to see how this left-hand side and right-hand side behave. So I write a over b as 1 plus x, where x is greater than or equal to 0. Okay, then this left-hand side is log 1 plus x. So if you Taylor expand, you get this. The right-hand side is this is x, and this is x plus 2. So the right-hand side is precisely this. And if you Taylor expand, you get this. So they are very, very similar. They are the same up to the second order. But if you compare the third order, this one is bigger. And now you're convinced that this inequality must be valid. So you just define your fx to be something you want to be, something that you want to be positive. And yes, and then if you look at this quantity function, when it's 0, when x equals 0, and if you differentiate and compute, you get this expression, which is non-negative. So you can prove this. Okay, so you have this general inequality. So each term of this summation is lower bounded like this. So you get this inequality. Okay, so that was the basic inequality, and now I proceed to prove the improved Shiraishi-Saito inequality. So I again consider a general asymmetric jump quantity G, and I consider the expectation value of G, defined like this. And so in terms of R, you can write it like this. And again, I do this symmetry business. So since this is anti-symmetric when you exchange J and K, so this is the same thing J and K exchange. So you can write it like this. And then here you get this probability current. And what do you do? Well, this is very artificial, but you divide everything by this thing, square root of this, and you put this here, the same thing here. Okay, and then of course it's equal. And here then you use the Schwartz inequality. I think all of you know the Schwartz inequality. If A and B are real quantity, and then this is inner product, this is upper bounded by this. Okay, so here this is A and this is B. And so you square this, you get this, and you square this, you get this. And of course, this is the familiar one. So we have proved that this summation is upper bounded by sigma t. Okay. And so that's why we did this. And as for this is a new thing. So this is a kind of expectation value of G squared. So we call this quantity xi G of t. Okay. And so what we obtained is this inequality. The expectation value of any jump, the expectation value of any jump quantity, absolute value, is upper bounded by square root sigma times this new quantity xi. And this xi is defined in this way, but now J and this GJK squared is symmetric in J and K. You can rewrite it like this. So this is, in a sense, the expectation value of G squared. But this is not very important, and I want to claim that this quantity is in general finite. It does not diverge. And in particular, if G, the jump quantity G, is upper bounded by G naught, and the escape rate is upper bounded by lambda naught, and then, first of all, if you look at this, then you can pull this out to sum like this, and then you can sum over k to get this escape rate here. Okay, and then since escape rate is upper bounded and this sums up to be 1, you get this simple upper bound lambda naught times g naught squared over 2. So this tells you that this convinces you that this quantity xi is in general finite. Okay, so this is the same inequality is written in this way as a lower bound of sigma t. So we know that sigma t, the entropy production rate, is non-negative, but this is an improvement. Okay, this says that whenever you have non-zero current, so you can measure whatever you current you're interested in, but if you get a non-zero current, and then this is non-zero, and of course this is finite, so this tells you that sigma t is non-zero. Okay, so so entropy increases whenever you have non-zero current, and this is an improvement of the well-known inequality. Okay, and this is the basic inequality, the improved Shiraishi-Saito inequality, but I'm going to use in the following part the time average version of the improved Shiraishi-Saito inequality. And so this is the inequality we have. So you take the time average from 0 to tau of this quantity. So you integrate this like this. And then here's the integration version of the Schwartz inequality. And again, let f and g be real valued functions. And then this inner product is upper bounded by this. Okay, so here you can plug in this, you can simply put tau here. And so this is upper bounded by the time average of sigma and psi. Okay, now we look at the time average of sigma. And so if you recall equation 2 in page 20, what is this? Well, this is almost nothing, but let's recall it. This is page 20 of part 4. So sigma t is defined in this way. So this is simply the expectation value of theta, but this is the time derivative of this function here. So if you integrate this over time, here you simply get the difference of s. It's here. Okay, so here you simply get the difference, and here you have the time integration. And now we want to make this tau to be larger and larger and take this limit. Okay, and then since the Shannon entropy is always bounded, so this difference is always bounded. So if you make tau goes to infinity, this vanishes, and you only get this thing, which is the averaged entropy production in the bath, or the averaged mean or the average dissipation in the bath. Okay, so this is a good news. As I said before, theta, this is a sort of thermodynamic quantity. Okay, and here we have this annoying information theoretic quantity, and we usually do not know how the Shannon entropy of a non-equilibrium state behave. But here, and of course we needed the Shannon entropy to come here, but at this stage, and if you take the infinite time average, then this Shannon entropy safely vanishes. Very nice. Okay, and this is simply the time average of xi, and of course it's upper bound, it's bounded. So we get this time averaged version of Shiraishi-Saito inequality. And what does it say? Well, since this is non-zero in general, this implies that whenever you have a non-zero average current, then it implies that you have non-zero mean dissipation. You have non-zero entropy, average entropy production in the bath. Okay. Now, in the next video, I'd like to discuss in the coming 2 videos, I'd like to discuss 2 applications of this inequality.